Okay, we're happy to have Piotr Gruza here to talk on separations between categoricity-like properties of first-order theories. And as you see, it's joined with Leszek Kołodziejczak and Mateusz Wewick. Go ahead, Piotr.
Thank you very much. Thank you for having me. Okay, as you said, this is a joint work with Leszek Kołodziejczak and Mateusz, and let's start with some preliminaries which we'll need later. So we say that a theory A interprets a theory B if and only if there is a translation from the language of B into the language of A, such that A proves all the translations of all axioms of B. So if we want to interpret in a theory B, then we need a formula delta, which is provably in a non-empty subset of tuples of the universe of A. We need another formula eta, which defines an equivalence relation on delta on the subset defined by delta, which we will use to define equality of the theory of B, of the language of B. And for each symbol of the language of B, we need a formula. And when we have this, we can translate every formula from the language of B into the language of A in such a way that propositional connexes commute with this translation, and quantifiers are changed into quantifiers which are relativized to delta. Similar definition we can make for models, but with the change that instead of probability, we say about satisfiability. So now delta is just a subset of tuples, and eta is an equivalence relation. And we say that a model M interprets a model N if and only if the quotient structure is isomorphic to N. Okay, so if we have two interpretations, I1 of C in A and another interpretation I2 of D in the same theory A, then we say that these interpretations are isomorphic if and only if there exists a formula that is provably in A and isomorphism between the structures given by I1 and I2. So it is provably an bijection between sets of equivalence classes given by A1 and I2, such that some further conditions are satisfied. And when we have this definition, we can say that a theory A and theory B are bi-interpretable if and only if there are interpretations I1 of B in A and I2 of A in B, such that their compositions are isomorphic respectively to identity interpretation on A and identity interpretation on B. Similar definitions we can also make for models with suitable changes, namely instead of formula which is provably an isomorphism, here we have a formula that is an isomorphism in K between the structures. And we have also analogous definition of bi-interpretability of models. Bi-interpretable structures can sometimes be considered are equivalent or of the same power or something like that. For example, if K and L are parameter-free bi-interpretable, and by parameter-free bi-interpretable, I mean that both interpretations and both isomorphisms, formulas defining this isomorphism isomorphisms are parameter-free. So if K and L are parameter-free bi-interpretable, then their automorphism groups are isomorphic. We need one more definition. So we say that A and A is a retract of B if and only if there are interpretations of B in A and of A in B, such that their composition is isomorphic to the identity interpretation on A. So this is kind of half of the biointerpretability. And we have similar fact. And we have a similar definition for models, of course. And we have similar also fact about automorphism group, namely if K is a parameter-free retract of L, where again, by parameter-free, I mean both interpretations and isomorphism are given by parameter-free formulas, then automorphism group of K is a retract of automorphism group of L. In particular, and we will use it later, automorphism group of K is isomorphic to a subgroup of automorphism group of L. And now we can go to the main topic. So tightness and neatness. So we say that a theory is tight if and only if for every two extensions of it, C and D, in the language of that theory, these extensions are biointerpretable if and only if they are equal. So this is a kind of local completeness in a specific category. Namely, if we think about category in which we have theories, okay, here we assume that all theories are deductively closed. So say we have a category in which we have theories and interpretations, but we think that two interpretations are equal if they are isomorphic. So in this category, if we have a theory which is tight, then if we take any extension of this theory and look at the surrounding of this theory, consisting of theories that are biointerpretable with this theory, then in the surrounding there is no other extension of A. So locally, this is the only extension of A, so this is kind of completeness-like, local completeness-like. We say a theory B is neat if and only if for every two extensions of it in the language of that theory, if C is a retract of D, then D is a subtheory of C. So again, this is a kind of completeness-like property, local completeness-like property, but we slightly extended the surrounding in which our extension is the only extension of this theory B. Semantic tightness and solidity are semantical counterparts of tightness and neatness. So we say that a theory A is semantically tight if and only if for every two models, K and L of this theory, and interpretations L in K and K in L, these interpretations make these models biointerpretable if and only if the first one is trivial. So in the sense that it is isomorphic to identity interpretation. So this is a kind of local categoricity-like notion. If we look at the category in which we have models and interpretations, but again, we think that two interpretations are equal if they are isomorphic, and we take a model of this theory and look at the surrounding of this model consisting of models that are biointerpretable with this model, then there is no different model. By what I mean that every model in the surrounding is actually definably isomorphic to this chosen one. Solidity is a counterpart of neatness, and so we say that B is solid if and only for every models of this theory, K and L. If we have these interpretations of L in K and of K in L, then if these interpretations make K a retract of L, then the first interpretation already is trivial in the sense that it is isomorphic to identity interpretation. To sum this up in the picture, so in other words, we can say, for example, that a theory is solid, that if we take any model of this theory and we are able to construct inside of this model another model of this theory, and inside of the second model, we are able to construct again an isomorphic copy. The star indicates that this is an isomorphic copy of the first model. And the first model knows that it is isomorphic to the third one. Then actually the first model already knows that it is isomorphic to the second one. It may be partly visible in the picture, but it's not hard to prove that solidity is the strongest property, tightness is the weakest property, and semantic tightness and neatness are intermediate properties. So solidity implies neatness, and solidity implies semantic tightness. And each of neatness and semantic tightness implies tightness. In this talk, I will try to give examples of theories that separate these notions. So for example, a theory that is tight but is not neat and is not semantically tight. So let's start with the first example. There exists a tight but not neat or semantically tight subtheory of PA that contains PA minus. And now we will prove this theorem. But first we need some reminders. So, and notations. So by z plus of x, we will denote the model of PA minus consisting of integer polynomials with a non-negative leading coefficient. If we have two theories, A and B, and a sentence, sigma, and all of them are in the same language, then by A plus sigma plus along sigma plus B along sigma, A plus B along sigma, by A plus B along sigma, we will denote the theory which say more or less, if sigma holds, then A holds, if not sigma holds, then B holds. And with this notation and this reminder, we can restate the previous theorem. So we will actually prove that if sigma is a sentence, every number is even or odd, then there exists a computably enumerable subtheory of the theory of the form PA plus theory of this model Z plus of X, which I will later call second standard model of PA minus. And the sum is along sigma. So there exists such a subtheory of this theory that contains PA minus and is tight, but not neat or semantically tight. So has this weakest property, but has no stronger properties. How will...
Piotr, sorry,
Yeah?
can you go back to the previous slides?
Yeah.
You can see again what this addition of
addition
is. Yes, right.
So this is addition.
All right, the notation here. Right. So then we can take a look again at the theory you defined there. Right. How does it work? Right. Go back one, just one.
It's like a
So
case
this is
distinction.
Yeah, so this is a theory which say if sigma holds, then PA. If not sigma, then theory of the second standard model of PA minus.
I see. So all right. So this just splits this into two. All right.
Yeah.
Okay, thanks.
Yeah, so the point of this construction is that we take two models. Here, this is a standard model and the second standard model. By second standard model, again, I mean this model consisting of polynomials. And we take these models, and these models, each one separately, is kind of well-defined, by which I mean that a theory of which of these models is, for example, solid. And the relation between models is such that if we take this kind of sum of theories of these models, then we obtain theory which has some interesting properties. Okay, so let's come to the proof. So what we need to prove? First, we need to prove that this theory which is still slightly unspecified, that this theory is not neat and is not semantically tight. So first we'll prove that it is not semantically tight. So we'll prove that the standard model and second standard model are bi-interpretable. And it will be enough because standard model is a model of our theory, and the second standard model also is a model of our theory. I haven't specified this theory, but I said that it will be a subtheory of PA plus this theory of the second standard model. So, okay. First, we, of course, can notice that there is interpretation of the second standard model in the standard model, because basically in the standard model, we can talk about sequences, so we can talk about polynomials. We have also a interpretation in other direction, namely in the second standard model, we can define the standard cut by the formula saying for every z smaller than x, z is even or odd. And this formula defines a standard cut.
And and the ordering on Z plus, is this part of the language?
Once again?
You have the ordering on Z plus X, so is this part of the language?
Yeah. This is a Z plus of X is a model of P minus. So we have.
Oh, I see, right. Okay.
Yeah. I mean, addition in this model is just polynomials addition, and multiplication is, I will maybe go back, and we are here. And this is just polynomial addition, and multiplication is just polynomial multiplication, and we can, using this, define, for example, order. Okay, so we have interpretation from standard model of second standard model in the standard model, and of standard model in second standard model, and it's not hard to see that there is a definable isomorphism from the standard model onto the copy of the standard model, which is interpreted in the second standard model. So basically, if we look at this interpretation, then we can map 0 to 0 of this model. Do you see my pointer?
Yes.
Okay. So we can map 0 from this model onto the 0 of this model, and nth element onto the nth element of this model, basically because we can talk about sequences in this model. We can notice also that as to this point, this interpretation and this isomorphism was defined by formulas without parameters. Okay, so now we need to define an isomorphism from the second standard model into its copy inside the standard model. So we claim that there is such an isomorphism, and this is because basically PA minus is sequential. So in the second standard model, we can talk about sequences, and because in this model there is definable the standard cut, we actually talk about real finite sequences, so we can talk about polynomials. And when we take as a parameter a polynomial x, then we can define every element by a formula of some bounded complexity. So because in this model we have every element is definable from this parameter, so now we can construct a map from this model to the model which is interpreted in the standard model as follows. We take an element, we look for the smallest definition of this element in this model, and this has to be a standard definition, and we map it to the element which is defined by the same formula in the model which is interpreted in the standard model. Okay, so these models are bi-interpretable, so we proved what we wanted. Okay, by looking closer at the proof, actually we can see that theory of natural numbers is actually a retract of theory of the second standard model, and this is because in this three first lines we didn't use parameters. So first interpretation is without parameters, second interpretation is without parameters, and this isomorphism between standard from natural numbers onto the standard cut of the second standard model is also parameter free definable, so we can actually write this on the level of theory of natural numbers. So we have this already proved. So by this we showed that this theory which are thinking of is not neat. So we proved that our theory is not semantically tight and cannot be neat. Now we will prove that we can choose this theory to be tight. Okay, so we will prove the following two lemmas. First, we will prove that there is a computably enumerable subtheory of the theory of the second standard model that has no extension, that is a retract of an extension of PA. And then we'll prove that there is a computably enumerable subtheory of the second standard model that is tight and contains PA minus. And it will be enough because if we then take as our theory of the form PA or union of these theories which are given by these lemmas, then this theory will have these properties which we want, which we can now see. So let say A be a theory which is defined as I said a few seconds before. And let C and D be extensions of this theory. We have three cases. C and D can be both extensions of PA. Then we are done because PA is tight. So if C and D are extensions of D, then actually C and D are equal. Okay, so there is second possibility. C and D can be both models of can be both extensions of the theory which is given by this lemma. And then again, we are done because this lemma say that this theory is tight, and we know that tightness is closed under taking extensions. I should say this before. If we take a theory and we take an extension of it, and this previous theory was tight, then the bigger theory also is tight. And this calls for all categoricity-like properties. So, okay, so we had these two cases, and we have also the third case. So C can be an extension of PA, and D can be an extension of theory given by these two lemmas. But then, D is a retract of C, and C is an extension of PA. And first lemma say us that that cannot be the case. So we are done. So now we need to prove these two lemmas. Okay, so let's start with the first one. We'll prove that there is a computably enumerable subtheory of the theory of the second standard model that has no extension, that is a retract of an extension of PA. Okay, so first notice that the second standard model is not a parameter-free retract of N. And this is basically true because, and this is true because automorphism group of this second standard model is non-trivial. For example, the x and x plus 1 have the same type, and we can map x to x plus 1 and extend this to automorphism. So the automorphism group of this model is non-trivial, and automorphism group of standard model is trivial. And as our theorem from the preliminaries said, if we have two models, here this is first model, this is second model, and first is a parameter-free retract of second, then automorphism group of first one is a subgroup of the automorphism group of the second one. But second one here has trivial automorphism group, and first one has non-trivial, so it cannot be the case. Okay, so we proved that this is not a parameter-free retract of N. Now we can extend this to show that actually second standard model is not a parameter-free retract of any model of PA. How we can prove it? So say K here is the second standard model, and M is some model of PA. And that we have situation as in this picture, so we have here definable isomorphism from K to K star. So now, because in K we have definable shortest cut, and the theory of this model is sequential, so we can embed this shortest cut of K onto some initial segment of M. The argument is similar as to this given for which I given in one of the previous lemmas. Okay, so we have a definable map from this shortest cut onto an initial segment of M. Because this is a model of Peano arithmetic, so there is also a definable map from M, it's definable in M, definable map from M onto an initial segment of K star. And it has to be actually an initial segment of the shortest cut of K star, because otherwise M could see an cut in itself but this is a model of PA, so there is no cuts in it, definable. Okay, so we have definable embedding from the shortest cut of K onto M, and definable embedding from M onto initial segment of the shortest cut of K star. So now we can use this isomorphism, actually reversed isomorphism, to construct an embedding from the initial segment of K, this shortest cut of K, into the shortest cut of K. We just compose these two embeddings with reversed isomorphism, reverse this isomorphism. But this is the shortest cut, so this has to be onto. So that means that all of this embedding has also to be onto. So we have actually, so this embedding in particular from the shortest cut of this model was onto this model of Peano arithmetic. So actually they are isomorphic. So because K was the second standard model, M is actually a standard model now. And we proved that this cannot be the case in the first point. Okay, so now we can construct our theory. So to our theory, we put the following axioms. So we put there PA minus. We put there that this formula delta defines the shortest cut. Actually, this is an infinite collection of sentences. And we put another infinite collection of sentences. Each of these sentences say that, okay, so for every collection, for every finite set of formulas I and j, and a formula phi, we write a sentence which say I does not give us an it's not the case that this whole points hold simultaneously. So I is an interpretation of PA minus. This can be written just as a sentence because this theory PA minus is finitely axiomatizable. Secondly, J is an interpretation in the structure given by I of the isomorphic copy of the universe, which we write just by indicating that this formula phi defines a isomorphism from the universe into this copy given by J. So again, this is a finite. This is just a sentence. And we write also a sentence which say that some particular formula, psi I, which we can compute from I, is an isomorphism from delta onto I. So the sentence says there is no such I, j, and phi, such that I is an interpretation of PA minus, j is an interpretation in I of the isomorphic copy of the universe, and such that psi is an isomorphism from delta onto I. Okay, so now I said that we can write this as a sentence. Now, what we want this theory to mean. So, okay, maybe go back to our second standard model. So in second standard model, when we start, say K is the second standard model of PA minus. When we started in second standard model, and say here I1 is actually I. So in second standard model, if we had two interpretations, and first is I and second is J, and this isomorphism is given by phi, then if this is a model of PA, then actually we can, from the formulas which gives us this interpretation, we can compute an embedding from the shortest cut of K onto an initial segment of M. And in case M is a model of PA, we actually know that this embedding has to be onto. So this psi I is a formula which is say basically that this is an embedding that gives us this embedding from the initial segment of K onto some initial segment of M. Okay, and we now want to prove that this theory has the property as we want. So that any extension of this theory is that this theory has not an extension that is retract of an extension of PA. Okay, actually we will prove that any model of this theory is not a parameter-free retract of a model of Peano arithmetic. Okay, so say now K is a model of this theory. I say that M is a model of Peano arithmetic, and K star is a model of this theory. So now, because here we have shortest cut given by delta, so, and this is a model of PA minus, so there is a definable map from this cut given by delta onto initial segment of M. Similarly, we have an embedding of M onto an initial segment of the shortest cut of K star. And making, okay, and repeating our previous argument, we can see that this embedding actually has to be onto. Okay, but in our theory, we have that if this embedding is onto, and I is an interpretation of PA minus, this is interpretation of PA. So in particular, there's a interpretation of PA minus, and we have inside the interpretation J, which gives us isomorphic copy of K star, then then we obtain a contradiction. Yeah, our theory says there is no such a situation. So the point of this construction is that because in case of second standard model, we have this property, we can put to our theory enough informations to get the same behavior of our model as the second standard model behaves. Okay, sorry for tangling up this. Okay, so we proved that this theorem, so we proved that there is a computably enumerable subtheory of the second standard model that has no extension, that is a retract of an extension of PA. Okay, now we want to prove that there is a computably enumerable subtheory of the theory of the second standard model that is tight. And how we can do this? Well, first, we can recall that the second standard model is bi-interpretable with the standard model. And actually, it's almost parameter-free by interpretable, by which I mean that both interpretations and one of the isomorphisms is actually parameter-free. And the second one can be seen actually as a family of isomorphisms. So there is a definable subset of the second, without parameters, of the second standard model and a formula such that if we take any element defined by this formula and we take then the second formula with this parameter defines an isomorphism from the second standard model onto its copy inside N. So it is almost parameter free. And using some similar considerations as before, we can actually define a theory that is similarly almost bi-interpretable with PA, where again, by similarly almost bi-interpretable, I mean that we can have two interpretations which are really interpretations in models, one isomorphism which is really isomorphism, and the second isomorphism is not exactly isomorphism, it is rather a family of isomorphisms with parameters, but set of parameters is provably non-empty and definable by a formula. And then we use the fact that PA is solid and that solidity is closed under by interpretability. So the point here is that this model is almost parameter-free by interpretable with the standard model. And actually, it has counterpart on the level of PA. So there is some computably enumerable sub-theory of the theory of this model that is almost parameter-free by interpretable with PA. So we can transfer the solidity of PA onto to prove that actually this theory can be actually solid. So in particular, it can be also tight. And I will not go into more details here. Okay. So we proved that there is a tight but not neat nor semantically tight theory. And the whole point of the argument was that we taken two models. Each of them was theory of each of them was actually solid, but they had different but automorphism group of one of them was trivial. The automorphism group of second one was non-trivial, and we combined them to obtain a theory that was tight, but not semantically tight and not neat. So now we can actually ask for which n we can we make this, can we improve this theorem, namely for which n is there a tight but not solid, not here should be not neat or semantically tight subtheory of PA that contains I sigma n. And at the moment, I don't know the answer. I hope, I think for every n we can find such a theory, but at the moment, I don't know. Okay. So now we will prove another theorem similar. So we will prove that for every positive natural number, there is a tight but not neat subtheory of PA that contains B sigma n. So we can have arbitrary strong theories that are tight but not neat, but I don't know if these theories can be made to be not semantically tight. So here we only know that it has this weakest property, which is tightness. It does not have this property, which is neatness, but we don't know if it is semantically tight or not. Okay. So now we will maybe not in full detail, prove this theorem. So first, we need another reminder. So let's fix a natural number n and a model of I sigma n. And by I n plus 1 to n plus 1 of k, let this denote the set of this x's in k, which are bounded above by a sigma n plus 1 definable in k element. Then this is a sigma n elementary substructure of k that satisfies b sigma n plus 1 and not I sigma n plus 1 if this is a non-standard model. Because that might be the case that our sigma n plus 1 definable elements of k are actually standard. So now if there is sigma n plus 1 definable in k non-standard element, then this model satisfies b sigma n plus 1 plus not I sigma n plus 1.
I think you're
Yeah.
missing a slight additional condition. If a k satisfies just I sigma n, then I think there's also the possibility that your cut is all of k again. So you don't want this cut to be all of k. Otherwise, you might not have sigma n plus 1 collection. It's just a minor thing.
Yeah, you're right.
But it's not literally true, I think, what you said.
Yeah. Okay, next reminder, arithmetized completeness theorem. So if A is a computably enumerable theory such that PA proves that it is consistent, then we can actually interpret this theory in PA. And having this, we can again restate. Okay, we need one more definition before we restate the theorem. So for a given natural number n, let Kn be the model of I sigma n plus x plus naught con I sigma n plus x obtained by using this arithmetized completeness theorem in n. So this is non-standard model satisfying. Yeah, maybe we need to make here an adjustment, but we can make this construction in such a way that this model is a non-standard model that satisfies b sigma n, b sigma n plus 1, but not I sigma n plus 1. And by I n plus 1, we will denote this initial segment given by sigma n plus 1 definables of this chi n. And having this definition, we can restate our theorem. So we will prove actually that for every positive natural number n, there is a computably enumerable subtheory of the theory of the form PA holds or theory of this IN model holds that contains B sigma n and that is tight but not neat. So
but I guess n is not 0, right?
yeah, positive natural number.
Right.
Yeah, for every positive natural number. Yeah. Yeah, and again, construction is similar. So we take two models. One is standard model. The second one is this special B model. And we say that each of them separately is somehow has well-defined theory. That is, this theory is tight or some reasonable fragment of this theory is already tight. But when we combine them, we obtain theory which has some different properties here. This tight but not neat theory. Okay, so first we need to prove that this theory is not neat, because then every subtheory of this theory also cannot be neat. Okay, so similarly as before, we can see that theory of the standard model is a retract of the theory of this IN model. So, okay, first of all, we need to note that there is an interpretation in the theory of natural numbers of the theory of this IN model, and this is by the construction of IN. Basically, we used arithmetized completeness theorem, and so we actually could do this on the level of PA. Okay, so we claim that there is also interpretation in other directions, so that in the theory of IN, we can interpret theory of the standard model. And this is because the standard cut is parameter-free definable in this IN model. Basically because sigma n elements are cofinal in IN by construction. Okay, so we have interpretations in both directions. And similarly as previously, there is a map from the theory of the standard model to the standard cut in this interpreted structure by the reasons which were given in the previous proof. So this is similar, basically. Okay, so now we want to prove that our theory, we want to construct a theory that is tight, and we know that it will not be neat already. Okay, so the scheme of the proof is similar. So we have two lemmas, which are basically analogous to the previous ones. First, we prove that there is a computably enumerable subtheory of the theory of IN that has no extension, that is a retract of an extension of PA. And then we prove that there is a computably enumerable subtheory of the theory of IN that is tight. And then we combine these lemmas exactly as in the case of this theory, which we proved that was tight but not neat or semantically tight. Okay, so let's prove the first lemma. First, we need a reminder. So for every positive number n, if we take a model of b sigma n plus not I sigma n, and c and p from M, and a formula with phi of x, y, z, as you can see, then we know that this formula with these parameters p cannot define in M an injective multifunction from n into a bounded fragment of M. Okay, and we will use it now in the proof. So we want to prove that there is a computably enumerable subtheory of theory of IN that has no extension, that is a retract of an extension of PA. So actually, we can prove that there is no model of b sigma n plus x plus not I sigma n with the shortest cut that is a retract of a model of PA. And this is true because of this cardinality scheme. So say K is a model of b sigma n plus not I sigma n, which has the shortest cut. So similarly and say that M is a model of PA. So similarly as before, K can embed its shortest cut onto an initial segment of M. M can embed itself onto an initial segment of the shortest cut of K star. So we have a definable embedding from the initial segment, the shortest cut of K, into itself. So it has to be onto because this is the shortest cut. So both these embeddings have to be also onto. So this is, so now we have n, so now we know that M is definably in K isomorphic to the shortest cut of K, which is a bounded segment. So if we have such a situation as in the picture, that in M we can construct an isomorphic copy of M, then actually we could construct this isomorphic copy of K inside of this shortest cut of K. So that would be a contradiction because K is a model of B sigma n plus not I sigma n. So there is no, in this model, definable injections from the whole universe to the bounded segments. And the shortest cut is definitely a bounded segment. Okay, so we have actually a computably enumerable subtheory of IN that has no extension, that is a Rishak of an extension of PA. And now we need to prove that there is a computably subtheory of this theory of IN that is tight. And again, we make similar argument as in the case of PA minus. So first, we notice that IN has the same theory as a structure interpreted in its standard cut. Okay, so in IN, the standard cut is definable by a parameter-free formula. So actually, we can write an infinite collection of sentences which say that theory holds, that a particular sentence holds in the whole in this model IN, if and only if it holds in this copy interpreted in the standard cut. And okay, so to our theory, we want to put that this is a model of B sigma n, but not I sigma n, that this particular formula delta defines the shortest cut. And for every sentence, we write a sentence which say that we put to our theory a sentence which say that this sentence holds in the whole universe if and only if it holds in the structure interpreted by a particular formula in the shortest cut. So say now that C and D are extensions of this theory. So C has its own shortest cut, I mean, as seen from the perspective of this theory. Similarly, D. So similarly as previously, actually we can show that there is a definable, that this shortest cut has to be definably in C isomorphic, because shortest cut of C can be definably in C embedded onto an initial segment of the shortest cut of D. The shortest cut of D can be definably embedded onto an initial segment of this copy of C, on the initial segment of the shortest cut of this copy of C. So we have similar situations as before. So actually, the shortest cuts of C and of D has to be isomorphic. And the theory of C is actually determined by this shortest cut because we written this directly into our theory. So we know that if a particular formula holds in C, then it holds in a structure which is interpreted in the shortest cut. So it holds also in the structure which can be also seen in D. So it has to holds also in D. And in opposite direction similarly. So C in D has to have has to satisfy the same sentences, so has to be actually the same theory. So our theory is tight. Actually, we didn't use this arrow, so actually we proved that this theory is actually neat. Okay, so we proved that this theory. Theorem. Okay. Okay, to once again sum this up. We have taken two models. We described their theories, and we demanded that their theories are coded in their shortest cuts, and that was enough to obtain a theory which we needed. Okay, so we know that for every n, there is a tight but not neat theory that contains B sigma n, subtheory of PA. But we don't know if the theory of any of these models is actually semantically tight or solid. So we don't know still if this is true. Okay, so we can ask the following question: for which n is there a semantically tight but not neat subtheory of PA that contains B sigma n? And actually we can prove if we can realize this in one of those models I've just described or similar models. Okay, so today I've talked about the relations between these four properties: solidity, neatness, semantic tightness, and tightness. And first, we showed an example of theory that is tight, but is not neat and is not semantically tight. Then we looked closer at this arrow, and we showed that theories which are tight but not neat can be arbitrarily strong in some sense, but we don't know if these theories are of this kind, so if they are semantically tight but not neat, or are of this kind, so are not neat and not semantically tight. Next week, I'm going to start with an example of a almost arithmetic theory that is neat but is not semantically tight. Actually, we will prove the following theorem. There is a computably enumerable theory in the language of PA with one constant added that is neat but not semantically tight. The proof of this theorem will rely on the following lemma, which is, I think, interesting in itself. So we will prove that there exists a computably enumerable type T over PA, such that for every model M and every two elements C and D from this model, if both these elements C and D realize this type, then first, both are undefinable without parameters and have the same type. So there is a computable type such that in a given model, such that in every model, if we take this type, implies the whole type of this element which satisfies, which realize this type. So yeah, so if we have an element which realizes this type, then this determines the whole type of this element. Okay, and next, I will show, probably not in full detail, that when we that all possible separations as marked in this picture can be realized among subtheories of ZF with the axiom of infinity negated. And yeah, and that will be the end of next talk. Thank you for your attention. Yeah.
Okay, let's thank our speaker. Let me look for my little clapping emoji. All right. Thank you, Piotr. And well, we can have time for questions.
Yes, I have a question. As you said, these properties are like categoricity.
Yeah.
But I can imagine an opposite kind of property, which would be some sort of saturation, which says there are many non-isomorphic bi-interpretable models. Is there such an idea?
Could you repeat? I don't understand.
Well, could there be a property which is in a way the opposite of categoricity of categoricity-like properties, and it would say it would guarantee that there are many non-isomorphic bi-interpretable models, mutually bi-interpretable models of the theory.
Well, I haven't thought about this before. So I don't know. Yes, I haven't thought about this before. Yeah, here the aim is rather to give some show that there are some shadows of second order categoricity in the case of first order theories. But probably I don't know. Probably we could write, but such a property in a similar manner, but I need, yeah, but I don't know if they were interesting. But, yeah. I don't know if it's if this answer was satisfying.
So I think the person to ask about that would be either Albert Visser or Ali Inayat, because these notions were, I think, from Albert Visser, and then I can't remember the year, but then Ali Inayat had proved that PA and Z2 are tight, and then
Yeah, solidity, neatness, and tightness were defined by Ali and Ayat. Albert Visser proved that PA is neat, and Ali and Ayat later proved that PA, Z2, ZF, KM, and some other theories are actually solid. And later, semantic tightness was, I think, introduced by Humkins and Freire. Yeah.
Well, I have a question.
Yeah.
No, I didn't have time to think through, but that these are interesting results if you're interested in sort of division lines between various those notions and you those notions of categoricity and to separate them. But for those of us here who are sort of interested in models of PA or fragments, the proofs are probably more interesting than the actual results. The fact that those things exist, that they are fine, but the proofs are interesting, and you select particular theories, and you combine various known and some new results about thereby interpretability. So this might be an interesting subject on its own when you sort of take two of those theories. You take a strong one, a PA, and you sort of match it with some like PA minus and then the fragments. But there may be some kind of more general theme here that you have some kind of theory about pair, something that you can say about two theories together. So for example, and I guess probably the answer is no, but if you pair instead of PA, you take a stronger fragment of arithmetic and a weaker one, would some of those results still hold? Like, B17 versus B3, B sigma 17 or things like that, right? Because if you have this pairing of PA together with fragments starting with PA minus and then you go up, but what if you take two different levels of say like B sigma n or I sigma n? Is there any interesting that you can say about those theories with respect to your operation?
Well, so if we take just I sigma n or B sigma n, then these theories are not even tight.
Right, all right. So this is all. So you have to start with PA to have something that's tight. Is that
Not necessarily?
I
I
see.
mean, we need to start with some particular models, which has interesting properties. I mean, as seen together, and this both can be models of one can be a B model and second can be an I model, but both has already some interesting properties. So it's not like that we can choose, probably it's not like we can take arbitrary models of B sigma n, arbitrary model of I sigma n, and say something about this. We need to choose some special models.
I see. But if you choose something a model and its extension or a model of its submodels, then you already know how one sits in the other. But I guess the theories of those pairs are not really that well developed. It's probably the kind of, from classification point of view, they're essentially unclassifiable, I guess.
Yeah. Here in the case of arithmetic, these results which I show are maybe not very scattered, but we use different techniques in different contexts. I mean, in each context, actually, these results are about automorphism groups of these models, because cardinality scheme is actually something which we can derive from some properties of automorphism group of this model. So in each case, we talk about some automorphism groups of these models, but still, there is no uniform way we don't have uniform way of stating such theorems. During the next meeting, I will show that there is an easy uniform way to make the separations in case of ZF without infinity. But in arithmetic, then it's question, can we obtain the similar patterns as we can obtain in the set theory? Can we obtain similar patterns in arithmetic, in fragments of arithmetic? Yeah.
Right. But because sort of just to follow up on what I was saying, it seemed to me that your argument, it was important that you have the standard model ready all the time to compare those initial segments, the standard cut and defining the standard cut. in all of that. So I understand, it's all very specific, so everything's specifically chosen
Yeah,
to.
the point is that actually we know that there are solid subtheories of PA, for example, which does not interpret PA, but actually every subtheory of PA, interesting subtheory of PA, which is solid, we actually, in every example of such a theory, we have this, in every model of such a theory, we have the smallest cut. We don't know, as for now, if there are theories, proper subtheories of PA that are solid and that are really much weaker than PA. That is that they have models which does not interpret models of PA.
Mhm.
And this is some problem in giving examples and thinking about classification in general case. The
Mhm.
point is that we have really problems about saying things about, in general, about interpretations in arbitrary B models, for example, or I models.
Mhm. Mhm.
There are, as far as I know, there are no many results about interpretations in models.
Mhm.
Yeah,
I see. Right.
yeah,
And Piotr, I have one complaint, if I may.
yeah,
No, because you managed to prove, to present quite a lot in 1 hour, but the proofs were not easy to follow. Especially for those of us who get a little older, because you introduce certain definitions and some of them are new, so you have to keep track of what's what. And then if you explained everything in all those little diagrams, then you know intimately what's going on there. But if you just talk about it without the sort of saying what's what, it was all fine because you said a lot, but it wasn't that easy to follow. I'm not sure if it was not that easy to follow for everyone, but it was difficult to follow
yeah.
for me. So sometimes it's better perhaps to say less and then perhaps present one proof and then to say, oh, the other proof is somewhat similar, but to spend more time like presenting on a slide that now we're talking about this, and here's this is standard model on the left, and this is this other thing on the right. So it's sort of easier to follow. No, it wasn't. Though it was an excellent talk in a sense because you told us a lot, but it wasn't easy to follow.
Yeah, I agree. I really tangled at some moment. I'm sorry for that. Yeah.
No, no, that's fine.
Are there any other questions or anything? Okay, let's thank Piotr again, and as he
Thank you.
mentioned, he will come back next
Yeah.
week to complete. It looks like he'll complete the picture on on all these different relationships. So thanks again, Piotr.
All right.